a very special episode of Nova. I am Pat.
And I am a guy who loves science, but I always say stuff like that. So Pat, you can say who I really am now.
Yeah, he is Zachary, and we are, we're from a little show on the internet called Zachapat, which you can watch by going to youtube.com/Zachapat, and we're also in partnership with RandomVideoSketches, the channel you're watching this video on. But I don't have enough time to advertise. Welcome to Nova. I know I don't watch it, but I've seen some at school. But I know there is one guy, the only other guy on here who does watch Nova, right?
What?
Do you watch Nova?
No, not really.
Well, do you like Nova?
I watched the episode of Hurricane Sandy, but that's it.
But do you like Nova?
Yeah.
Alright, we're on Nova. So, here you go.
Okay, we're going to start with chemistry. We're going to do a basic run-through of the periodic table with neutrons, protons, electrons, and all that.
Alright, let's start with hydrogen.
Okay, hydrogen is the lightest element. It's a gas in its natural form, and its atomic symbol is H. It has 1 proton, 1 electron, and 0 neutrons. It has, is that it?
Yeah, that's good enough.
Name? Yeah.
Alright.
Name, protons, neutrons. Oh, wait. Atomic weight of 1.0. Oh, yeah. For these atomic weights, I'm rounding off, so it's not going to be exact.
2 is helium.
Okay. Helium is one of the noble gases. That means it has complete outer shell. 2 electrons, 2 protons, 2 neutrons. The fun fact, the nucleus of helium is an alpha particle, so we might explain more about that later. But its chemical symbol is He, and it is a gas at its natural state, like I said, and its atomic weight is 4.0.
Alright,
But
so...
as you know, the atomic weight is always going to be protons plus neutrons. Since it doesn't say neutrons on the place where I'm looking to get all these facts, since I only know the order of the elements, I'm neutrons by subtracting protons from atomic weight.
Okay. Alright, lithium.
Okay.
Lithium is number 3.
Lithium symbol is Li. It has 3 protons, 3 electrons, and 3 neutrons. And it is a solid at natural state. And I'm pretty sure that's it.
How about the atomic weight?
The atomic weight, I said that's... Oh, no, I didn't. 6.9.
Okay, I have 6.941, but whatever. Alright, next is, beryllium. I don't know how to pronounce that.
Beryllium.
Beryllium.
This has 4 protons, 4 electrons, and 5 neutrons. The atomic weight is 9.
No, it's 9.012182!
No, 9.0.
I have 9.01.
It doesn't matter. I'm just looking at an approximation. I'm rounding it off. It has Be for its symbol, and it is a solid at natural state.
Alright.
Boron. It is not boring. 5 protons.
Wait, what'd you say?
5
What'd you say? Wait.
And 5 electrons. Its symbol is B. It is 10 atomic weight, and it is a solid at natural state.
Alright, carbon. I named them.
You probably heard of it, and it has 6 protons, 6 neutrons, 6 electrons, and 12 atomic weight, and it is a solid at natural state, and what else? Oh yeah, C is its symbol.
Alright, nitrogen.
Nitrogen has 14 atomic weight, 7 protons, 7 neutrons, 7 electrons, and it is its symbol, and it is a gas at common state.
Alright, oxygen.
Oxygen has 8 protons, 8 neutrons, 8 electrons. Its atomic weight is 16.0. It's gas at natural state, and it is its atomic symbol is O. I think that's it. Yeah.
Okay, fluorine or whatever.
It's 9 protons, 9 electrons, and 10 neutrons, and it is 19.0 atomic weight. Atomic symbol is F, and it is a gas at natural state, apparently. Fluorine is like toothpaste.
Let me guess. Neon's 10 of something.
Yes, neon is 10. Neon has 10 protons, 10 neutrons, 10 electrons. The atomic symbol is Ne, and it's a gas at natural state because it's also a noble gas. And its atomic weight is 20.2.
Alright, sodium. Nah! Okay, sodium.
Sodium is 11 protons, 11 electrons, and, let's see, 12 neutrons, it says.
Well, I'm getting that too.
So, that would be
Yeah.
Na. Its atomic weight is 23.0. It is a solid at natural state, and that's it.
Alright, magnesium.
12 protons, 12 neutrons, 12 electrons, atomic symbols, and
Sounds like
the atomic weight is 24.3. What else? It is a solid at natural state.
Aluminum, or however you pronounce that.
Okay,
What is it?
aluminum.
Okay, there we go.
Aluminum.
Okay.
It has 13 protons, 14 neutrons, but 13 electrons. 27.0 is the atomic weight. Al is the atomic symbol. It is a solid at natural state.
Silicon.
Silicon has 14 protons, 14 neutrons, 14 electrons, and its atomic weight is 28.1. Sorry for the mix-up. Its symbol is Si. If I didn't already mention that, it is a solid at natural state. Phosphorus. It is 15 protons, 16 neutrons, and 15 electrons. Atomic weight, 31.0. Atomic symbol, P. Atomic state. Atomic state. Natural state is solid. Your turn.
Alright, sulfur.
What?
Sulfur.
Okay. Sulfur. It is 16 protons, 16 electrons, and 16 neutrons. And its atomic symbol is S.
S.
And its atomic weight is 32.1. And it's a solid at natural state.
Alright, next is chlorine.
Chlorine.
It's poisonous!
Yeah, well, I guess. There's a few elements that's poisonous. Like, the radioactive ones are radioactive. And, arsenic's pretty poisonous, but we'll get to that later. Chlorine, 17 protons, 17 electrons, and, 18 neutrons. And, it is a gas at natural state, and its symbol is Cl. Argon is 18 protons, 18 electrons, and 22 neutrons. Its atomic weight is 40.0, and it is a gas at natural state. Its atomic symbol is Ar. Potassium is number 19, 19 protons, 19 electrons, 29 neutrons. Its symbol is K. Its weight is 39.1. It is a solid at natural state. Calcium is number 20. It's 20 protons, 20 electrons, and 20 neutrons. Atomic weight is 40.1. Its symbol is Ca, and its base solid at natural state. Scandium, 21. That's 21 protons, 21 electrons, and, let's see, that's 24 neutrons. Its atomic weight is 45.0. Its symbol is Sc, and it is a solid at natural state. Transition metals, because it's a transition metal. Seriously, they're all going to be solid at natural state if they're transition metals. Titanium, that's 22 protons, 22 electrons, and 25 neutrons. Atomic weight 47.9, symbol Ti, and it is also a solid at natural state. Vanadium is next. That's 23 protons, 23 electrons,
speaking of...
and that would be 27 neutrons. Its symbol is V, and its weight is 50.9, and, what else? It's a solid at natural state. Chromium, next. Chromium.
Okay.
Okay, 52.0 is its atomic weight. I don't know why I'm announcing it first, but I am. It has 24 protons, 24 neutrons, and, that would be, 28 neutrons. 28 neutrons. And its, symbol is Cr, and it's a solid at natural state. Manganese is, number 25, 25 protons, 25 electrons, and for neutrons, that would be 29. 29 of them, neutrons. It has 54.9 atomic weight. Its symbol is Mn, and it's solid at natural state. Iron, this metal is pretty important. It's 26 protons and electrons, and it would be also 29. Okay, now, that would be 4, 24, and, so it would be 29 neutrons. The atomic weight is 55.8, and it's a solid at natural state, and its symbol is Fe. Cobalt, number 27, it is 27 protons and electrons, and for neutrons, that would be, 31 neutrons. It has 58.9 neutrons, 58.9 atomic weight, that's what I meant to say. Its symbol is Co, and it is a solid at natural state.
January 4th, 2013, we'll do another one of these on Nova, and we'll finish off this.
Yeah,
that's big news.
But if you cannot wait, you absolutely can't wait, and you really, really want to know, you can't wait, just look at the internet. There's periodic tables all over the place.
Go to
I even drew like a few.
ptable.com.
Periodic tables.
Yeah, go to ptable.com. That's where I'm on right now, and periodic table's right here, so go to it. It's good.
But if you're sure you can wait, and you just don't care about the internet or seeing them, you want us to explain them because you are a auditorial learner, not a visual learner. I'm a visual learner, but I'm just saying, some people like listening to
Like me. I'm an auditory learner,
they
so...
might want us to explain it, so they might want to wait for that, as the visual learners might want to see it on the internet. And, so, And if you're a body kinesthetic learner, then just make a periodic table. Look at one and copy it down, and that will help you, because if you're body kinesthetic, you're good at moving and writing things down and maybe color coding it. That's moving around while you're doing that, so you can do that. Anyway, we have to start astronomy. So, oh wait, no, we have to start physics. Physics we have to start.
Are mirrors physics?
Or what?
Mirrors, like how they work and all that.
Like the ones made of glass and all that?
Yeah.
No, mirrors. I thought you said windows. Mirrors are photons.
You mean
yes,
physics?
They are. I'll get to mirrors after I'm done explaining magnets.
Alright.
All magnets have a north and a south pole. And magnets, even if you cut them in half, will still have a north and a south pole. And if you cut those in half, they will still have a north and south pole. And repelling and attracting. If you put a north and a north or a south and a south together, they will repel. You can like put them together, but it's easier to put a north with a south, because then they'll just attract each other and go right together. And so yeah, that's pretty cool. So like I have a magnet in my hand right now, and let's just say I went and got a paperclip. I'm not actually going to do this, just an example. If I got a paperclip and I put this near the paperclip, usually paperclips have all jumbled up elements, which, like we mentioned in chemistry, they're all jumbled up, facing in different directions. Magnets, on the other hand, are all facing the same way. And so but the interesting thing is, if I picked up the paperclip, which is not a magnet, with this magnet, the paperclip would actually turn into a magnet, because the magnet would make all its
Someone needs to count how many times Zach is
that's pretty
saying.
interesting.
Someone has to count how many times Zach said magnet in that whole demonstration, because I have a feeling you'll be there all day counting the number of times he said magnet. Anyways, are you ready to do our next part? It's compasses, or magnets and compasses.
Yes, magnets are in compasses.
How does the compass work? What does the compass do? How does the compass work?
Are because Earth is a magnet. The North Pole is a North Pole is a magnet. The South Pole is a South Pole is a magnet. If we got into geology, I would tell you that this is caused because the outer core. I'm pretty sure it's the outer core. It might be the inner core, but I don't know. But somewhere in the core, I'm pretty sure it's outer core, but somewhere one of those is spinning in the opposite direction that the Earth is spinning, and that generates...
Yeah, that's the outer core. That's the outer core. Yeah. That I know.
The geographic North Pole is offset from the magnetic North Pole, but it still works since Earth is round. If Earth was flat, it wouldn't work. It would point northwest, or maybe even west. I mean, northeast, northwest, or maybe even east or west. And since Earth is round, it still works.
We're going on to mirrors.
Yes. Now, let's explain mirrors. Mirrors have something special in them. I don't know what. But neutrinos. I'm pretty sure they're neutrinos. Yeah, they're neutrinos. Neutrinos are like light things. I don't know what they are, but I'm pretty sure they have something to do with light. Yeah, they're light particles, I think. Yeah, I think that's what they are. But anyway, so, neutrinos like to bounce off of things. Some of them get absorbed, as you know, because, like, red, green, blue, light colors, scientific primary colors of light, blah, blah, blah. But when they get reflected, then your eyes see them as color. But neutrinos, mirrors reflect all neutrinos, not just, they don't absorb anything. So your color of neutrinos, when you look at yourself in the mirror, the neutrinos from you would go bounce off the mirror and come back to see an exact image of you. Since they don't absorb any color, you could see exactly what you look like. And that's pretty cool that they could come up.
Oh, wait. They want to also ask how one-way mirrors work.
Well, one-way mirrors work like this. One side, neutrinos can't get through. The other side, neutrinos can get through. So, if you're on one side, the neutrinos will all bounce back to you. But if you're on the other side, you'll be able to see through it since the neutrinos can actually go through. And, so, that's pretty cool.
Alright, are cameras physics?
Cameras! Well, a little bit.
Alright, we can go into
I'll
some...
explain the physics part. The physics part is where light, visible light, from the electromagnetic spectrum, which we will probably explain, that would be, I'm pretty sure it's, what was first? I know it's second. I'll have to look nowhere, because I can't look anywhere.
Okay, what is touch?
Touch, is, like, you mean like feeling, like how...
I actually have, because I haven't been talking very much. I'll actually just explain a little fact I know about touch.
Well, after you're done, I just have to say something before you explain it. Touch and feel are two different things.
Okay, anyways, here's something that I just found out recently. Touch, like, nothing ever touches. Ever.
What?
The atoms, but, like, attract to the opposite, atoms or something. Like, how your butt is probably touching the chair right now, or...
No, actually, my feet are touching the floor.
Yeah, your feet, or your butt's touching your chair, I meant, or your feet are touching the floor, whatever you're sitting on, or you put your hands together and push them really hard, and you're not actually touching, because, and you can't see it, but by a very, very, very minuscule atom, just one little atom, it's actually apart, although you don't see that, but, they're actually you never touch anything. Which is sad, because then every time you hug someone, or kiss someone, you're not actually touching. But, apparently it's close enough to cause a reaction, so, good enough. Yeah, but, yeah, you never actually touch. You're always an atom away. But since it's so close, the reaction that, happens between it, like you feeling something, or bumping into a car and possibly dying if you don't wear your seatbelt. Wear seatbelts! Continuing. Yeah, it's just so not much of a difference that in no way at all do you realize anything. But, yeah, just thought I'd mention that. They don't actually touch.
Okay, now I have to explain that touch and feel are two different things. Okay, first I'll explain touch. Touch is when two things meet each other in the universe. Like, if I threw this paper, or threw a paper on the floor, then the paper would be touching the floor, since the paper is on the floor, and they're right next to each other, and let's just say that's touch. Feel is a human sense, where, if a body part is touching something, like I'm touching this chair right now, I feel the chair. So, when you're touching something, you don't have to be feeling it. But when you're feeling something, you're always touching it.
Yeah.
Unless you're feeling the emotions, but seriously, this is physics, not biology. So, when we say touch and feel, we're not meaning touch like you're sad and happy at the same time, and we're not meaning feel like feelings and emotions. We're meaning touch like when two things meet each other in space and feel like a human sensation. sensation when a human touches another human or an object.
Alright.
So I'm feeling and touching the floor, but that shoe is touching but not feeling.
Alright, is it possible to capture a single photon of light?
What?
Is it possible to capture a single photon of light? And I actually know the answer because I'm reading this off something.
Well, I'm pretty sure that is not possible.
Oh, it actually is possible because recently, about 2 months ago, the 2012 Nobel Prize in Physics was given to David Rhineland for capturing a single photon of light. And that's what I was just reading.
I'm pretty sure that can only happen if you're almost blind.
What is E equals MC squared?
E equals MC squared is energy equals matter times the light speed squared.
That's a lot of...
Energy equals matter times the speed of light squared.
Is prediction possible? Can you actually for sure predict the future? Can you be psychic?
Can you be psychic?
Yeah.
As far as I know, you can predict the future, and you can have visions of what, things happen, but you can't actually know 100% sure that, you, will always be right 100% of the time.
Because...
Nothing is ever 100%.
Yeah.
It could be 99.9%, but nothing will ever be 100% in science. So if you hear us say 100%, then just know it's not 100%, it's 99.9.
What if the Earth were hollow?
If the Earth were hollow, then I'm pretty sure that we would all be dead. Because we would fall down through the solid rock, go to the center of the Earth where pressure was so extreme from air and rock on top that that we would probably be dead by then. And if we somehow survived, then we would go through the other side of the Earth and into space, where all those gross things would happen.
Yeah.
I mean, I'm pretty sure your muscles turn inside out or something, and I'm pretty sure you don't want that.
All right.
So,
is it possible to drill a hole through Earth?
well, no, because either the drill would burn and you would run away somehow, or the lava from the mantle will kill you instantly. What?
Now if...
Ooh.
What if,
What?
if somehow, I know it's not physically possible, but if somehow someone was to drill a hole through the middle of the Earth and you jumped in, what would happen?
Well, you would be killed by the mantle, incinerated by the inner core, and nothing left would be left to reach the inner core. Oh yeah, when I said inner the first time, I meant outer.
Okay. Is there a fourth dimension?
There is. There might be 5 dimensions. I don't know. Yeah, there's 5 dimensions. Okay. Dimension 1. It is a straight line. It only has width, or it only has height.
Alright.
A 2-dimensional object is like a drawing on paper. It may look 3D, but it's 2D.
How?
When it has height and width, that would be, but not depth, which means it doesn't stick out. It may look like it, but it doesn't.
Alright.
3-dimensional is what an ornament, or a piece of candy, or even you, or a hairbrush, or a phone is. It's like, height, width, and depth. The 4th dimension is kind of weird. I mean, not weird, like I'm trying to insult it, just weird, like... It's not really normal 3D and 2D. 3rd dimensional, 4th dimensional is called tesseract. It's kind of, we can't see it to us, but it's kind of like, it's a cool thing. One-dimensional wouldn't cast a shadow. Two-dimensional casts a one-dimensional shadow. Three-dimensional casts a two-dimensional shadow. Fourth-dimensional casts a three-dimensional shadow.
And so on.
Fifth-dimensional doesn't cast a shadow at all, because I'll get to that. Pretty sure, unless you somehow got it to be a solid object, except it isn't. It's just there.
So what is an example? Wait.
If you brought it into our
Zach,
normal 3D world,
Zach,
it would create a black hole.
Zach,
I don't know why.
what is an example of a fourth-dimensional object?
I don't know. We don't really. It's kind of like three-dimensional, but one's inside the other, and it's like going inside and outside, and it's like kind of weird. I don't know. Just if you look up a picture of a tesseract on the internet,
I got
then
one.
that'll have a better visual.
Way convenient.
So, now, fifth-dimensional is called time. Yes, the ordinary time, like clocks and all that. It's, like I said, it's just there. It does not usually interact with, the normal three dimensions and the fourth dimension, but, it is very important because, well, you know, time machines, they're bad.
Nope. We're not talking about time machines. Off topic.
Oh, I know, I'm just saying, like, it doesn't matter. I'm just saying that time, without time, we'd all be stuck in position, we couldn't be able to think.
Alright.
It's good to have time.
One more thing.
There's only one way that time does interact with space. Space is the first four dimensions. And when you do that, you get an invisible thing called space-time.
Oh, wow! Wow, that's amazing, because the next question was, what is space-time? So continue.
Okay. Space-time is related to astronomy a bit. Space-time is in space. When you have an object on space-time, it will make a little dent because of its gravity. Like, if you have the sun on it, it would be a little bit deeper hole than Mars would, because the sun has more mass, which means more gravity, so the hole would be deeper, but Mars doesn't have as much mass, so it would be a little bit higher. A black hole, since it is, I'm pretty sure it is the most dense object in the universe. It actually creates a hole in space-time, which is, like, it's just kind of extraordinary. It's just not normal. Hello, and welcome to our astronomy portion of the show.
Okay, so we're welcoming our special guest, Michael from Vsauce. So let me kick it over to him, and he will talk to you for the next 10 or so minutes about black holes and how exactly it would feel to travel into a black hole and the experience.
I know how it would feel. Very painful.
What we can compare it to, the experience, what it would look like if someone went into a black hole, all that stuff. You ready?
Yeah.
Alright. Unfortunately, this part of the video was cut out due to copyright reasons, but we highly recommend going to bit.ly/108KRSC to watch Michael from Vsauce explain black holes, because we will be talking about it throughout the astronomy section of this video. Thank you. Okay, that's the end.
Well, I think that would be pretty interesting. That was a pretty interesting video and stuff.
Yay.
Black holes are, like, way easier to imagine. If you imagine this little space-time thing, which is pretty much just a imaginary fabric or invisible fabric that runs through the universe, and stuff that has gravity, like everything, because everything has gravity, would bend space-time a little bit. The So the sun, since it has more mass, more gravity, would bend space-time more than, let's say, Mars or Earth. Or
Yeah, that was
maybe
actually...
even a person, like me or the TV, me even, or whoever's watching this, or even a balloon. It would bend space-time even a slightly bit. Now, black holes are much more dense, much more massive, and their gravity is so great that it actually makes a hole in space-time.
Yeah.
So if anything really fell into the hole, then that would be the end of you.
Yeah, that was actually visual. There was a comparison of a human to the sun to a black hole, and you can see the huge difference in how the black hole actually made a hole where the other ones just made a gap. So, yeah, you can, that's actually in the visual, so that's pretty cool. He didn't actually really talk about it, but
yeah,
a lot of
like,
stuff in visuals.
The other gravity, like the sun and me and you, they just make, they don't make, like, a gap in space-time. They make just a little dent in it, like a bending.
Yeah, yeah, a dent. I couldn't get the word. But, yeah, you want to talk about the video now?
Yeah.
Alright, so, go ahead.
Well, I think the video was pretty interesting.
Yeah, it was. Also, just feel like saying this because, just in case you, want to know, that is actually one of the YouTube videos. He posted a YouTube video, like, a few days ago, because he didn't think we were returning to this, but now it's on YouTube, too. Also, if you want to check him out, it's on youtube.com/vsauce. And he has posted a total of, let me see, can't find this, come on. Well, he has almost 3 million subscribers, which is a lot. And about 330 million total video views, just felt like pointing that out while I look for how many videos he's made. Oh, look here. He has made a total of 257 science videos. So, those are really interesting. He uploads a new one about once a week. So, if you want to check that out, you can subscribe to him at youtube.com/vsauce. I just thought I'd point that out. What?
Last pizza, like Pizza?
No, Vsauce. Like VSAUCE. Vsauce.
Okay.
It's a strange name.
Couldn't quite hear that, but I will take your word for it.
Yeah, it's actually quite a strange name that I didn't understand. And there's actually a video that I never watched about like why he chose his username to be Vsauce. Also, if you're interested in like online games, if you're a guy that likes playing games online and looking at interesting websites online, he has a playlist for that too about like online games. It's called Dawn. Things you can do online.
Let's talk about some other astronomy stuff. I mean, enough about black holes and stuff.
Yeah.
We have to talk about some other stuff. Astronomy's not all about density, black holes, mass, matter.
Yeah.
There's other things to it.
Well, you want to answer questions, and then that will, like, get our ideas going?
Yeah.
Why is the sun so hot?
The sun is hot because it's a star, and it's made of plasma, and everything's hot at the core, and mantle, and whatever in the Earth, so the sun's layers are also hot, except it's much hotter because obviously the crust isn't normal.
What is a nebula?
Oh, like planetary nebula or cat's eye nebula?
They just asked what is a nebula, so I'll answer both.
Planetary nebula is where there can be white dwarfs in them, and like when stars die, some of them become white dwarfs and have a planetary nebula around them, which are pretty cool to look at. And so if you've ever seen a picture of one, then they look pretty cool. And I actually don't know what a cat's eye nebula is. It's something, it's almost the same, like slightly the same, but not the same.
What is the Big Bang Theory?
The Big Bang?
Yep.
The Big Bang was the beginning of space time, matter, everything. I mean, the universe originally was just a singularity, and there was nothing around it. I mean, it's hard to imagine, but there was nothing except for that one singularity. And suddenly, one day, it exploded. Well, not one day, obviously, because it's, there was no time yet. But then after it exploded, there was time and space and matter. And in a fraction of a second, there was antiparticles and particles and lots of stuff.
Okay, how long ago was the universe created?
About 14 billion years ago.
Yeah.
With a B.
What is a singularity?
A singularity is a small point in a place or in space, which there was none of. I can't find the right word without using space, which there was none of at the time. So I'll just say a singularity is an extremely small point in a place, or an extremely small point. I'll just say that.
Is it possible to live on Mars?
Well, with protection, definitely, as long as you had a heater with you, because, I mean, it's cold on Mars. Without protection, you'd probably freeze to death. Although, we're sending spacecraft to Mars pretty soon, and we might build, like, cities there that have big heaters.
Oh, that would be so cool. That would be so cool if we could actually, like, visit Mars or something. That would be awesome.
So, that's the thing, so...
Yeah, so, time for biology.
Hello, and welcome to our biology section of this show. Today, we will be starting with the integumentary system of the body system, and you probably have no idea what I'm talking about because no part of the word gives any clue as to what's in it, except that skin has weird names, like tissue of skin is like, starts with an E. I forget what it's called. It's like, anyway, well, integumentary is the skin system. Skin, nails, hair, anything that protects your body. Let's start with skin. Skin, 3 layers, epidermis, dermis, and everything below that. Epidermis, top layer of your skin, it's all dead. The top layer of your epidermis, because your epidermis also has layers, includes all dead skin cells which are constantly falling off. The bottom layer of your epidermis, or parts of the bottom layer, or maybe even a few layers above that, contains the pigment melanin, which, when exposed to sunlight, makes your skin a darker color. And now on to dermis. Dermis is the layer below the epidermis. I don't really have much to say about it, but if you get a burn on your skin that's like 3rd degree, that, I think, is the burn that extends down to the dermis, and that would be pretty painful. Your skin chars and blisters, so that would be painful. Below that is like all your stuff, like sweat glands. I think that might be the dermis, but I know there's like pain receptors there. The dermis is the biggest layer, but the pain receptors are, well, they're pain receptors. They feel pain and send signals to the brain, and that tells you when you're feeling pain.
And that's useful.
Yeah. But some burns, like the big burns, can actually destroy your pain receptors, which wouldn't actually, you wouldn't feel that at all since you don't have pain receptors. Nails and hair are both made of collagen and keratin, and nails are actually skin that hardens, and hair is just hair. Nothing really to say about that.
Alright, move on.
Okay, next body system?
Yep.
Next. So, under the skin is all the rest of the body system, including the cardiovascular system, more commonly known as the circulatory system. In the center of it is the heart. obviously, which has 4 sections. The left aorta, right aorta, left ventricle, and right ventricle. First, they pump unoxidized blood to the lungs to get oxygen, and then go around to any cell, I guess. Or, yeah, then they go back through the heart to any, and then go out of the blood vessels to any cell that needs it. It could be any type of cell, nervous cell, red blood cell. Actually, no, red blood cells carry the oxygen. Yeah, so not red blood cell, but red blood cells carry it to nervous cells, skeletal cells, any type of cell. And then it goes, the cell gives them their carbon dioxide, which they transport back to the heart and then back to the lungs where they, deposit it so that they can not have it anymore. And then they go back to the heart where the cycle starts all over again. So blood is in your cardiovascular, and that pretty much means that, blood is made of red blood cells, or erythrocytes, leukocytes, or white blood cells, and platelets, which help your blood clot. But there's also blood plasma, which is like the liquidy stuff that's mostly made of water, which consists of most of your blood. Also, I was going to say something. The cardiovascular system is named this because cardio is heart, and vascular is blood vessels. Three types of blood vessels, which are atrium. No, not atrium. There's, what was the 3 types? There's veins, capillaries, and arteries. Arteries transport oxidized blood to cells. Veins carry carbon dioxide blood back to the heart, and capillaries are like when arteries get smaller and smaller to get to the cells. Arteries actually have so much pressure in them that if you cut one open, the blood would squirt across the room, which is just pretty weird. Skeletal system is where you make the red blood cells in the bone marrow, in many parts. Skull, cranium is the same thing as the skull. Skeletal system because it's a skeleton. And I don't really have much to say except that it supports your body and makes blood that is in your circulatory. Anyway, you probably heard that it supports your body and can move, but it's really the muscular system connected to the skeletal system that is doing all the moving. Muscular system is pretty much just muscles, biceps, triceps, any type of thing, quadriceps. They are connected to your bones via ligaments, which connect your muscles to your muscles. The bones also have cartilage on the ends of them, which help reduce friction and help the muscles get more moving places. On one side, your muscles contract and shorten, while on the other side, your muscles relax and get bigger. So when I touch my arm, my upper arm, which would be the part that would be when I am walking normally would be the upper arm. When I lift my arm, the top is getting contracted, while the bottom is obviously relaxing. And then when I bend my arm the other way, it's the opposite. The bottom is contracting and the top is relaxing. Sometimes your muscles get attacked, and this causes stuff like like when your immune system attacks your muscle cells. So immune system is white blood cells, leukocytes. So first, there's white blood cells in your blood, B cells that that stands for something, I forget, but that goes and looks for any invading antigen on the germ. Germs enter your bloodstream only if they can get past the detection of your skin, your nose, because the mucus traps things in your nose, and you sneeze them out, or stomach acids, and then they can get into your bloodstream. When in your bloodstream, they can, if not spotted, they split and make you sick, invade your cells, do whatever. Now, whenever these cells recognize that you're sick, they send out antibodies, or they create antibodies, which latch on to the antigens on the invading germ. They're kind of like a red flag or a flag or something. Then they call T cells, which are also leukocytes, to come and eat them. Yes, they actually do eat them. And if a germ with antibodies on them is not caught, if enough antibodies are on the antigen, they can actually neutralize showing by themselves. Afterwards, the B cells.
We have to move on.
Okay. The B cells, called memory cells, also travel looking for invading germs. Next is lymphatic. Lymphatic blood leaks from your bloodstream often, and cells deposit waste into it, which kind of sounds gross at first, but it's actually not that gross. It's just like carbon dioxide and stuff. So then, they just pretty much, they stay there until a lymph vessel, kind of like blood vessels, but for lymph, picks the lymph up, which would be the blood with stuff in it, and now it's called lymph. And so it goes through the lymph vessel to what is called a lymph node, which cleans it up and puts the blood that is now clean back in your bloodstream. So that's the lymphatic system. Not very much to say about that. Digestive. Digestive, you all know what this is. You eat via your mouth, saliva, your teeth break the food down. It goes down your esophagus, which only takes about like 5 seconds, into your stomach, which then moves as hydrochloric acid to dissolve any food. So then it's like it stays there for 4 hours, then travels into the small intestine, where stuff from the gallbladder and the liver are waste during the chyme, which is now in the top. So the small intestine picks up most of the nutrients in it, which then travels to the large intestine, also called the colon. No, the small intestine is not called the second colon. And the small intestine is actually way bigger than the large intestine. The large intestine is just wider. The appendix on the edge of the large intestine actually has no purpose. The large intestine picks up the rest of the remaining nutrients and water and dries it out. When it gets to the end of your large intestine, then you're ready to go to the bathroom with the excretory system. But that's solid waste, so what about liquid waste? Liquid waste, when you drink, goes to your kidneys, filters it out, good from bad. The bad waste products go to, have stuff at them from the liver, gallbladder, and stuff. And that is now called urea, which, has dead red blood cells in it, which make it yellow. And so that goes to the bladder. A healthy bladder can hold 16 ounces of that before you have to go to the bathroom. And there's little muscles near cardiovascular go together. Like, a lot. Respiratory gives the cardiovascular system oxygen. So, how it works is your diaphragm, which is under your lungs, goes down, and that makes your lungs bigger, which, due to air pressure, makes air go in your mouth and down your trachea into your lungs, which goes into a little sac called alveoli, where there are blood vessels where the blood gets oxidized and deoxidized, or decarbon dioxide. So after you breathe in, your blood takes that, but then blood comes in that's carbon dioxide. So then, when it's in your blood vessels and gives zero carbon dioxide to your lungs, this carbon dioxide is a poison to us. Your diaphragm gets bigger, your lungs get smaller, and the air is forced out up your trachea and out of your mouth. And that's the respiratory system. That's pretty good explanation. Now, the endocrine system, well, that's how you can do all these things. They consist of mostly glands that send out hormones, like pancreas produces insulin, pituitary gland is the master of it. Pituitary gland kind of gets signals from the nervous system, tells the glands when to produce what hormones. Like, when are you going to produce insulin? When are you going to produce adrenaline? So that's pretty much how. The pituitary gland is right below your hypothalamus, which is around your brain somewhere. Hypothalamus, I'm not sure what that does. I think it does something like control your emotions, but I am not sure. So, I think that's what it is. But anyway, we have all that, and that's the endocrine system. The endocrine system can do this, of course, because the pituitary gland tells them to, but then how does the pituitary gland know if it is not a brain? And so it becomes the nervous system tells it what to do. Nervous system is 3 parts of your brain: cerebrum, cerebellum, and brainstem, your spinal cord, and lots of nervous passageways, which are just nerve cells. The endings of them are called dendrites, which get electrical signals from the brain and pass them on to maybe a muscle to move a muscle, or they are in your brain so that they can have thoughts, or you can have thoughts. And also, there's like a special coating on them, I forget what it's called, but it protects the cells from electrical signals. Some things like Alzheimer's disease break those coatings and cover them in black, and then you forget stuff. But, so like, the information goes to your brainstem, which travels down the spinal cord and out to your body, like for a muscle or a gland to produce hormones, or anything really. So it's pretty much like the headmaster of your body. It tells you what to do. Like, if you're not, you have to have your nervous system tell you to nod. If you want to swing a baseball bat, your nervous system has pretty weird. Probably know what I'm talking about. These are weird.
They are really weird.
Yeah. Well, that's the body systems.
So, we are down to our last 3 minutes of this Nova video. So I think it's time we conclude the video as a whole. So, yeah, this was 2.5 hours long. That's a pretty long time for you to watch
I thought
us.
it was only 2 hours long.
Yes, that's what I meant. 2 hours. That's still a pretty long video. So, yay, you got through this whole video. We'll definitely make more in the future, sure. Because these are fun to make, aren't they, Zach?
Yeah.
Alright, so, yeah. I am Patrick.
What?
What's your name, guy?
I'm Zach, obviously.
Yeah, and,
I probably already told you that.
and we'll see you sometime in the near future. Bye, guys.
And hopefully by that time I won't have a cold.
Yes. Alright, bye, guys.